Okay, so good morning, everybody. So another colloquium of this month. It's a pleasure to have today a joint colloquium by André Lessa from Sao Paulo and Wolfgang Waltenberger from Vienna. So they are both visiting professors at the moment through the CPTGA and the Enigmas programs in UVA, which has led to this month-long Models collaboration meeting. So, as I said, Andre is from Sao Paulo, so he actually did his PhD with Howie Bear in then still Florida.
It started in Florida,
ended in Oklahoma in 2011. So lots of SUSY phenomenology, dark matter phenomenology, related with SUSY. So he then moved back to Brazil, first directly to Sao Paulo as a postdoc, and then he became a professor at Sacco Andre, UFRPC, recently. Wolfgang is so Andre is by training as jurist and also by heart. Wolfgang, he is a CMS experimentalist from Vienna, so he did his PhD at the HEFI in 2004. He's still at the HEFI. The experimental careers are much more straightforward.
Not always.
And he actually introduced the concept of simplified models to CMS. And we are all collaborating very intensely on models and on this idea of nowadays on this idea of statistically learning. The next standard model, which is the topic of today. People on Zoom, please. Okay, thanks.
Thanks. Okay, thanks a lot for the invitation. It's always a pleasure to be here. I've been here a few times, and I always enjoy the visits. And this month has been super productive and very nice. A lot of people coming in and out. We had very many fruitful discussions. So today we'll present this idea that we developed a couple of years ago, a year or so ago. And well, this is mostly work done by Wolfgang, and then I joined, and then Sabina, and it has been published last year. So I will start, like a couple of weeks ago, we had a colloquium by John Butterworth, and he presented this very nice map. So I'll start from here. And so he made this analogy of the experimental physics in the last couple of decades, and how it mapped out this subatomic world, right? And now we have a clear, more or less clear picture, which is the standard model. The last piece of land here was the Higgs that was discovered in 2012. And within this analogy, the LHC is our vessel that we are using to explore the unknown, right? So we are really going to regions that have not been tested experimentally before. And we can, of course, learn a lot with the LHC data, right? And we have already learned, of course, beyond the Higgs, which was a major milestone, but we also learned some things from no results. So before the LHC started, there was a considerable fraction of the high energy community, me included, that expected new physics to appear right away. So think that this vessel would crash against SUSY. Right? It was right there. And we had plots like this. Right? So we'd expect maybe, yeah. Okay, I don't have a pointer. Okay, we can use this maybe. Yeah. So, is there one here?
Physically, one, the bar there.
Ah, perfect. Much better. So, yeah. So we expected things like this, right? So this is just, it doesn't matter exactly what the variables here, but this would be the background, and this is a SUSY benchmark. So you'd see like these huge excesses in data, right? Or this is, I scan over some specific SUSY model, and this is the likelihood of the points, and you'd expect that SUSY would be lying here in masses around a few hundred GeV. right? So I'm not pointing fingers here. Like I'm the one who did this plot, so I'm guilty as well of these expectations, right? And we know after almost a decade of data taking that no clear evidence of new physics has emerged. And we have pushed some of these SUSY mass limits up to the TeV scale. Right? So some of the masses now have limits that go up to 1, sometimes even 2 TeV. Of course, this is not supposed to be readable, but it's just to illustrate how this expectation got frustrated by the data, and that's totally fine. That's something we've learned from the data. We have, of course, to take this with a grain of salt, because there are a lot of caveats behind these plots. But the big picture is whatever we were expecting to appear right away did not show up. Right? So, of course, within this context, is helpful to question our prejudices. Right? So, are we missing something? Could something behind in the data? Are we doing something wrong? Our approach is wrong. Could we change something? And typically, what we do more strongly on the pheno side of the community is to choose our favorite model. Then, do you need something? Okay. So we typically choose our favorite model, then we fix some of the parameters, look for promising signatures, simulate the signal using typically a Monte Carlo event generator, and compare against the LHC data. Right? And this works pretty well, and it has worked in the past if we have a very well motivated model that we expect to be the truth, right? Like we had with the standard model. Right? So this worked very well for the Higgs discovery, for instance. Right? Or it could have worked if SUSY was right there, and we knew exactly how it would look like. But that's not the case now. Right? We have to question our prejudices, and there are a lot of issues with this long path. Right? So, of course, there's a huge number of models. How can we know if we are choosing the right model or not? For each model, you can have an infinite set of parameters, so you could also miss new physics if you're looking only at some corners. There could be no obvious signatures that you're missing when you're trying to go along this path. This is quite CPU expensive, and of course, there's a huge amount of LHC data. What we choose, how we choose to look at this data also introduce some bias. So, what we started to investigate is what happens if the signal is not that evident. You don't have this huge access in data, but could be dispersed in many different channels. And also what happens if we have not considered the right model. Like we are too biased towards our favorite theory, and we are simply not considering all possibilities. So our approach here, our idea is exactly to tackle this type of issues. And what we propose is to do a more data-oriented model building, if you like. It has been considered before. At some point was labeled the LHC inverse problem, which is how from LHC data go to the BSM model. This is obviously not an easy task. It's very hard to do this. So our proposal was to simplify it a little bit, introduce an extra layer here. I'll explain in a minute what that means. But the idea is we can go through a subset of LHC data. Not in the future, we want to increase this subset as much as possible. But for now, we'll be considering searches with missing energy in the final state. So mostly SUSY searches. And then we'll present here a learning algorithm that tries to learn these proto models. Will become clear what I mean by that. And this is sort of an abstract layer, that's something in between observables and the full theory that we want to reach. Right? And the idea is that here we can be we can drop some of the theoretical bias that we have when we are constructing full BSM models or full theories. So what are these proto models? It's fairly simple. The idea is to have an intermediate step between this full theory and the data. And so instead of considering a Lagrangian, we go to something that connects more directly to observables. And so we parameterize these models by their particle content, but you see this is with very few assumptions, their masses, branching ratios, and production cross-section. And so we are not here making any considerations about possible underlying symmetries, gauge couplings, or couplings between these particles, and so on. These we really do take as free parameters, right? Which in a full model would be derived from the Lagrangian or the UV theory. Right? We do have some constraints. We assume there is a built-in Z2-like symmetry, mostly due to technical issues, and also because we are going to consider searches that look for this type of signal. The lightest particle has to be stable and neutral, right? Because if we assume it's Z2 odd, so it will not decay, so it can be a dark matter candidate, but we don't enforce that it is the dark matter. And we can, for those who are more familiar with simplified models, you can think of a proto model as a set of simplified models. So we have this, what we call a proto model builder, which actually randomly selects from a pool of particles and decays, and builds these models. Right? So we have a list, fairly reasonable list of possible particles, and this builder here will randomly select from this list and assemble models choosing masses, branching ratios, and cross sections. So the overall idea of the whole procedure that we're going to present here is we have this proto model builder, and it can create models. So the particle content is not fixed. It can add or remove particles, change their masses, branching ratios, and cross sections. So it can create and change these proto models. So it will make random changes to the proto model. We test against the data. The data for us here is we use this models database to do this testing. Then we'll compute something like model score, how compatible it is with data, that we'll be discussing more detail in a minute. And we use this model score as a feedback for the proto model builder. So now it has some information about the model it created and tries to improve on it. Right? So the idea is that you do this sort of MC walk on the proto model parameter space, and the builder, after many steps, it learns the best proto model that fits the data. That's the overall goal of the procedure. Right? So in this sense, we reduce the theory bias because we are not fixing a model. The proto model can add and remove particles, change their branch ratios and masses, and so on. And we can make sure it's compatible with data and try to see if it converges to something that describes the data better than the standard model, for instance. Right? So a few more details about this Walker algorithm. The idea is, okay, you start with some initial proto model, a random one, always must have a light neutral particle here, so this is a requirement. And then it randomly selects particles from that list. So for instance, here it selected, I don't know, 2 additional particles. It randomly selects its branching ratios and masses, and then compute the proto model score. And based on it, it makes random changes on this particle. So it can remove or add particles. It can change the masses, branching ratios, and cross sections. And at each step, this is this proto model score is computed again, and it's used to inform the proto model builder of how well it's doing and how can improve in the next step. And so typically, if the proto model created in the step was worse than the previous one, the proto model will go back. If it's similar or better, it will keep this new proto model and then take the next step and see if it can improve on that or not. So what's driving the whole construction here, as you can see, is this proto model score. Right? This is what qualifies what is how good the proto model is to describe the data. So this is the essential component of the whole procedure, and now Wolfgang will discuss some details about it.
Yeah, so the most important thing is obviously the score, and in statistics terminology, I will call it a test statistic. And we want to identify, we're doing something, basically something a bit like an anomaly hunt, right? So we want to identify the largest deviation of the standard model hypothesis that can be explained by the simplest possible theory or a proto model, right? So it's sort of these two characteristics that need to be reflected by the test statistic or by the proto model score. So this is what it looks like. And you will see that, you know, the first aspect that I mentioned is it somehow needs to quantify the violation of the standard model hypothesis, and this is done by this likelihood ratio. This should be familiar to a few people if doing in data analysis. Likelihood ratios are very common. Yeah, and this is the ratio of, given the data, of the standard model hypothesis divided by the ratio of the by the likelihood of the proto model, right? And if the likelihood of the proto model becomes much larger than the likelihood of the standard model, we obviously have a stronger violation of the standard model hypothesis. This becomes smaller, so the overall test statistic becomes larger, right? So we want to maximize for this, but we want the simplest possible proto model. So basically, we quantify Occam's razor, the principle of Occam's razor, right? When in doubt, the simpler explanation is the right one, and this is done by these Bayesian type priors. So this pi is meant to reflect that it's something similar to a Bayesian prior for those of you familiar with Bayesian statistics. So it's our a priori. We assign an a priori probability to models. That's what it is, the Bayesian prior in this context. And we wanted to penalize for model complexity. But before I explain how the penalization works, so there is one additional aspect that I will go. There's actually two additional aspects that I would like to qualitatively explain. The one is the C. The C here stands for stands for complete, or a combination. It's a combination of likelihoods, and thus a combination of results in our database. So we combine results. And let me now explain the penalty term. So this is meant to penalize for model complexity, and the exact definition of this that we're using is actually a bit contrived, but I think for this talk it suffices to understand that it is something roughly approximately equal to e to the power of the number of new particles that are introduced. It's a bit more complicated, or it is more complicated than that, but roughly it's this. And those of you in statistics and data science, you should see that if I take the logarithm of this e to the power and I multiply with -2, I end up with something that is very similar to an Akaike information criterion like test statistic. It's also something similar to an Bayesian information criterion like test statistic. So it's very similar, essentially, to an information criterion, except that in Akaike you wouldn't have a likelihood ratio, you would only have a likelihood, but that's a detail maybe. Yeah, so, right, so we have this, our test statistic actually reflects the two sort of needs that we have. We want to identify the largest violation of the standard model hypothesis in our data, in our database, but we want to construct small models. So we want to maximize for this quantity for this test statistic here, ideally. Actually, we want the probability distribution over these, but never mind. So I already mentioned C stands for combinations. So we combine results, but we do not have the knowledge about the correlations between different analyses. So we need to play a few tricks here. And the way we do it is we try to identify those analyses that are approximately uncorrelated, and we only combine these. And a combination of results needs to be complete in the sense that if the machine can add, is allowed to add another result, it has to. And so we have not one test statistic, we have one test statistic for each combination, but the final, because we want to maximize for this quantity, the final test statistic is the maximum of these individual test statistics. And we play I would like to mention one additional trick that we're playing. So we only combine a subset of all these results, but we obviously want to make maximum use of the whole database. So the other results that are not in the combination, they do enter also in the test statistic as what we sometimes call a critique. So as a bit of an adversary that works against it and tries to falsify the proto model hypothesis at a certain point. And the way we do it is that we have this parameter of interest in the likelihood. It's something that measures the signal, a measure of the signal strength of the proto model, if you wish. We restrict the support of this parameter of interest such that all negative results, all exclusions are heeded, are taken into account. They're respected. So we do not violate any negative result. Yeah, we remain compatible with everything, with all the negative statements that we know about from the searches. Yeah, so what data do we use? Obviously, it's based on likelihoods, right? The L stands for likelihoods. So where do we get the likelihoods from? Well, the data we get from our database. So our database is actually something that Sabine, Andre, and I et al. Have been working on for 10 years now. So we've been busy collecting the search results. Currently, we have roughly results from about 50 CMS and about 50 Atlas published results. Yeah, this is a rough list. And in many, but not all cases, do we have sufficient information about the results that we can construct simplified statistical models? And if you have a simplified statistical model, we also have a simplified likelihood. In some cases, actually, in a very few select cases recently, we also actually have the full statistical model, but that's, for this project, that's just a side remark. So we have simplified likelihoods, we have simplified statistical models for many, but not all, results in our database. And now we need to combine them. And as I said, we don't have information about the correlation between analyses. We do not know. It's not easy for somebody outside of the collaboration, or impossible, more or less, or almost impossible. No, not impossible, almost very hard to figure out if, for example, every analysis sees a chunk or analyzes a chunk of the LHC data. The full LHC data is by now, going towards 1 exabyte. Every analysis only analyzes a chunk of the data, and an important question is, are these chunks disjoint for a pair of analyses, or are they not? If they're disjoint, we feel safe in combining them because they're approximately uncorrelated. If there's an overlap, if some of the LHC data is actually analyzed by both analyses, we don't feel safe in combining them, and the box for this given pair of analyses checks off as red. So we only combine those pairs of analyses that are marked as green here. And in the publication that we're presenting here, that we've done like 1.5 years ago, this matrix was actually more or less an educated guess by reading the abstract and reading the event selection in the publications. We've recently also here, we have an ongoing effort that we call TACO. One of the guys who actually did a lot of work obviously is Mexican. And the TACO collaboration was almost the entire TACO collaboration was actually here in Grenoble also for this 1 month stay. So we have been pushing this further. Recently, I mean, this is ongoing work, but the ongoing work is that you find these matrices systematically, not just by reading abstracts, but by simulating events and seeing if there's an overlap in the signal region. So we're trying to produce these systematically. And yeah, this is an ongoing effort that is also, we've also done a lot here. Yeah, and once we have this, we can combine and we can run the algorithm, right? And it's something like an MCMC walk. It's not an MCMC walk, but it's obviously very much lens borrows a lot of aspects from an MCMC walk. We walk this, right? It tries to find combinations that violate the standard model hypothesis. It tries to keep the proto model simple because Occam's razor. We validated, right? We synthesized, we produced fake databases where we know there is no BSM physics inside. We validated with databases where we know what type of BSM physics is in the database and saw if we can actually reconstruct it. If our algorithm actually reconstructs the truth, then we know because we put it in there. So this worked. You actually see there was a new high performance computing system starting in Austria. It was at that time, it was the largest in Austria, and I basically was their crash test dummy. So I burned the first million CPU hours on the cluster. So it's actually quite a lot of number crunching. And yeah, the question is, what did it find, right? So one run, we defined the notion of a run. One run is 50 of these walkers. One run consists of 50 walkers. That's semantically probably a wicked statement, but that's how we defined it. And yeah, and we had 10 runs on the actual, this is the result on the actual data. So you see that in all 10 runs, did the machinery, the algorithm feel compelled to introduce something I would call a top partner particle. Yeah, those familiar with supersymmetry, it's something like a stop. But for us, we didn't fix supersymmetry and we didn't fix the spins. So it could also be a same sign top partner particle, like in extra dimensional models, we wouldn't care. And the production cross-section was actually a free parameter. So it could have chosen the production, or it could have ended up with a production cross-section that would be compatible with universal extra dimensions. It so happened that it ended up with production cross-sections that were compatible with supersymmetry. So in all these 10 runs, did it feel compelled to introduce this top partner, right? And most of the time was roughly with mass of 1200 GeV, and once a bit lighter. In all the 10 runs, did it feel like, or was the penalty worth, was it worth the penalty to introduce a light quark partner? Yeah, so every introduction of a new particle has to be worth the penalty, right? There's something, it needs to pay a price, it needs to be worth it. The deviation from a standard model hypothesis needs to grow more than the penalty, or else it wouldn't do it. Yeah, so it always introduced a light quark partner particle. The LSP ended up always at around 200, 300 GeV. In one case, it actually felt like it's also worth the penalty to introduce a muon partner particle. So one nice thing is that in all 10 runs, we always get something more or less consistent. We get a consistent result, a robust result. And so what's the high score? What we call the high score model was the proto model that actually got the highest test statistic. And just for, for scrutiny. And it's this one. So it has this quark partner, top partner, or stop-like particle, down-like particle. And here are actually the analysis IDs of the dispersed excess. So what is driving the excess? You see, for example, that Atlas multi-check, let's take the second one here. There's a signal region where the Atlas people expected 526 events, but saw 611, right? And then there is 4 more of these. So this is sort of what constitutes the dispersed excess. But this is somewhat in tension with what the critic, what I previously called the critic, so the adversary found. The adversary says, and this is mostly driven by Siemens Multijet, there are some results where the upper limit they publish is below the expected upper limit, indicating that actually they saw too few events, not too many. So there is a tension between the actor, if you wish, in machine learning terminology, so the guy who identifies the dispersed excess, and the guy who tries to work against it. So there is a tension, there is a small contradiction, if you wish. I mean, nothing unusual within statistics. This will be another way of visualizing it. So the idea is a potential dispersed excess, right? What would a potential dispersed excess look like? And here are the two leading results, one from Atlas, one from CMS. So the idea is that you're asking yourself, is there an excess, something supporting the idea that there is an excess here? You would say, yeah, no, not really, maybe a little. And then you would go to CMS and you would ask yourself, is there something that supports the idea that there is new physics in this complicated result? And you would feel similar. You would go like, well, yeah, there's a bit too many, too often. Is there a bit too many events in the bins? But overall, not really an indication. But our idea is that, if you only properly find the right combination of these results and properly contextualize them, find a common ground on the theoretical, at the base of a theoretical model, then things might look different. That's the overall idea. And I already said that we have, for many but not all results in our database, we have statistical models. What that implies is that we actually we can construct sort of fake databases, synthesized, simulated databases of LHC runs. So we can pretend in our simulated world, we can think of, we have 1,000 universes, one LHC accelerator in each universe. We, in our simulations, turn off BSM physics. We produce results for each LHC accelerator in each of these 1,000 universes, simulated universes, and we see how the distribution would look like of our test statistic, because we have 1,000 of them. And then we can compare our real test statistic against this distribution of 1,000. And we can ask ourselves, how unusual or usual is our test statistic in this distribution under the standard model hypothesis? And this we also did, and we know that our estimate for several technical reasons, we know that our estimate is conservative. So what I just explained with the 1,000 LHC runs, or the 1,000 LHCs in the 1,000 universes, will be this orange line here. This is what we expected, and our observation sits here. And by definition, the p-value will be the integral of our observation to positive infinity, because the p-value will be the quantity that tells me what are the chances under the standard model hypothesis that you observe something, a test statistic of the value that you observed, or something even more extreme under the standard model hypothesis. So this direction is more extreme, and this area turns out to be 0.2. So we have a p-value of 0.2. That's very normal. We do know that it's conservative. So the smaller this p-value, the more violation of the standard model hypothesis, right? So if as soon as this p-value goes below, say, 0.05 or 0.01, we will start to be, really interested in why this number is so low. We know that this is conservative, so the actual number will probably be a bit lower. And so we expected a slightly higher number, but not something dramatically different. So the way we phrased it is in our paper at that time, it was, the first run, is we talked of a very small, very mild tension with the standard model hypothesis. And this is actually already everything. So at this time, we would have a proto model. Actually, we would also be able to give in the long run, we didn't yet discuss this so thoroughly in our first publication, but where we want to go is to not have a single proto model, but also have a probability distribution in the space of all proto models. That is more information, but okay, we have proto models. But our goal is not to construct the proto models, obviously. Our goal is to finally build the next standard model. So we need to make the connection still from the proto models with UV complete theories. And here also, like this month has helped us a great deal because we have first discussions started with Jonathan, who's in the audience, about how you would make this connection, how you would make this step. So you would have, we would have probability distributions, or we would have proto models, right? They look like this. And we want to translate them into Lagrangians, right? So the first thing we already started discussing is that we map the decays to operators. From the operators, we get terms in Lagrangians. And then we want to find, again, the smallest possible or the simplest possible Lagrangian that takes into account all these Lagrangians. And first we would, try to construct a simple broken Lagrangian. And from this we will go to an unbroken Lagrangian. And all this, and as soon as we have an unbroken Lagrangian, we can still confront it, or we still intend to confront it with all the relevant information about the next standard model that is not in our database. So LHC data that we do not have, we can now confront because now we have a model. Now we can go top down again. And we can also confront this with, data that is not from LHC, like G-2 mu, W mass, dark matter relic density, and so on and so forth. So these steps we will do the way, the very traditional way. The traditional way is this top down. You have a theory, you test it with your usual statistical tools. Yeah, and this is where it ends. What are we doing right now? What is also, there's a lot of stuff that we're doing, or we're starting, or we're discussing here in Grenoble with this month. And one big thing is, obviously, currently we still have this fairly narrow view of theories that exhibit a Z2 symmetry. That is a major restriction, actually, because of all the theories. I mean, the Z2 need not be implemented. So we're trying to get rid of this restriction, so we can describe all the results or most of the result of the SUSY of the searches at the LHC and most of the models. This is a big thing, so that will give us, widen our view quite dramatically. Once we've done this, obviously we keep adding results and results and results. Currently we stand at 110 or so. We keep growing. Just for technical reasons, we would machine learn this database, but that's only a technical aspect. And yeah, on the statistics side, maybe interesting is that we slowly move from simpler statistical models that describe, our data to more and more complex statistical models. And sometimes at full realism, the way that you also have it within the experiments via, for example, PyChef. And we improve our, combination metrics and so on and so forth. And I think this is everything. And we're very thankful for our sponsors, quite a few. So we have these funds, right? There is a French-Austrian fund with Sabine and myself. That part of this work actually is being covered by, there's this Ian Dupuis master project, and Andre and myself. We both are very thankful for all the funds we got by these various institutions, so Secretaria and Enigmas. And yeah, this will be everything, right? Thank you very much.
Thanks a lot, both Andre and Wolfgang. Do you have questions? Maria?
Yeah, just shout. So I have two questions.
Yeah.
The first one is, did you try to validate it by, for example, taking the background as the nominal expected, weighing around it?
Yeah.
Injecting a signal and seeing if your proto model does the.
Yes, absolutely, absolutely. We inject in, we have statistical models, so we can produce fake results, and this is exactly what we did. We have something in the backup, right? Yeah, we did all this. So this is, we injected, we found the high score model, right, on the actual data, and then we produced fake data with this high score model and saw and checked if, again, the proto model builder finds it, right, closure. And this is done here. Here we actually sort of artificially turned off statistical errors. Here it's with, here it's without the statistical errors, so it should, reconstruct it perfectly. Here it's with the statistical errors, so we expect that the reconstruction does not function 100% efficiently, right? There's reconstruction errors, and we could actually, quantify the reconstruction errors. Yeah, we did these types of closure.
But did you try also with more complex models? So see, for example, I don't know, injecting some SUSY signal, for example, say seeing if the the penalty for your complexity or things like that is.
So the models that we tried it with so far were fairly limited. This we could do also, yes. Yeah, absolutely.
So far, we only injected like simple signatures, like with 2 or 3 new particles. We did not try to have a full PMSSM that's distributed over signals from 19 different new states. This we have not done.
Yeah, we can. This would actually be easy for us. Yeah, we can do this. And one should actually see that a lot of the phenomena will not end up in the proto model, but rightly so, because there is not enough evidence. And some of the phenomena, if you take a typical MSSM model that is, within our reach, some of the phenomena, some of the particles, some of the branchings, we should be able to reconstruct, and some should remain, should be not worth the penalty. This is what will be the outcome.
Okay, I think that my second question was more about, do you have a bias by the analysis that you input in your data set?
Completely.
Yeah, because because if you have like 15 stop searches or something like that, you're more likely to find a top article, for example.
Yeah, I mean, this direction, no. You're not more likely to find.
Oh, well, yeah, because you will have fluctuations up and down. But so, in which sense then?
Yeah, in the sense that, like, all the results, RPV, SUSY, currently we cannot find because we don't have in a database.
Okay. Okay. Yeah, I see what you mean. But okay.
Yeah.
Not in a positive way, though.
The other thing we can penalize. We can penalize in the sense that if you have more results, there is a higher chance, it's just like the way we always penalize, like Lugauser effects and so on and so forth. If you have more results, there is a higher chance that one of them actually has a fluctuation. So you penalize for this in the Bayesian information criterion, for example, will take that into account.
Okay.
Something, this was a prototype run. But this will be something we will be doing in the second iteration. Currently, it's not penalized for the number. But this.
I mean, one obvious bias is, of course, comes from the quality of the experimental information, like whether it's possible to construct a likelihood from whatever results are given. Like in many cases, if we only have upper limits on cross sections on simplified models, from this we cannot construct a proper likelihood. So this enters only what Wolfgang calls the critic. Right. When we have efficiency map results, we especially including information on signal region correlations. The best case is, of course, the full statistical model as Atlas is providing now. Then this information is missing.
There is maybe one more aspect. Is that if you have 100 results, the chances that one of them is wrong is, I think, is almost a given, almost more or less a certainty. So we also want to make sure there is robustifications in the procedure, and we have some in place, and we'll increase them in a second iteration. So that in the critique, for example, this is already in place. In the critique, if one result very much contradicted, that alone may not be sufficient. Yeah. So you want to make sure that if everything else, if every other analysis actually is in favor of something and one is in disfavor, you may question the one. And this is also reflected, you want also reflected in the test statistics. So that you're you're robust against individual, inconsistencies within the analyses that actually should give similar results because they test very similar physics. It's robust statistics. Okay, sorry.
Let's try to keep.
Sorry.
So actually, it was along the same lines. I was just going to ask, did you try running the Volckers with different subsets of the analysis that we have in the database, and would it matter too much?
Good question. Notice we did not yet do.
Like maybe one really favors, like one subset really favors slope, but if one favors something completely. And
this we did not yet do. Yeah, good idea. Good thing too.
Thanks. I'm not too clear on how you define the branching ratios here. For example, if you have a new particle and it decays to multiple things, do you only consider a single decay, or do you consider all of these?
All of these, but the number of decays also enters the penalty.
Ah, okay. I see.
Yeah?
You want to try to keep the decays to the minimum.
Yeah, exactly. If you can take out the decay without any loss, then it will take out the decay. So that's why I said it. I only gave an approximate description of the test of the penalty term. In the detailed version, this actually appears. Also, production mechanisms are also penalized for example.
So I'm not sure I follow how you define the parameters of the penalty terms in the priors.
Yeah.
Isn't it arbitrary? How does it change if you change the parameter?
There is the archaic information criterion and the base information criterion. There are theorems, right? So archaic information criterion tells you, no, this is very wrong. There is an arbitrariness, but I think.
One more.
Down?
Yeah, there.
Yeah, right. So, if the number of degrees of freedom of your theory model was a clearly defined quantity, then archaic information tells you that if their penalty term is chosen such and such, you will be guaranteed to asymptotically pick the true model if it's in the set of models you're testing. Yeah? And base information criterion guarantees you that if you have several models, you're guaranteed to choose the most similar model to the true model in the sense of a Multilevel diversion. Okay, there is these theorems. So this is not arbitrary because I choose archaic and I know I'm guaranteed this asymptotic behavior. Where the arbitrariness, where there is a lot of arbitrariness, is how we think of number of degrees of freedom of a proto model, because that's not a clearly defined. What is it? How many free parameters are there in their artificial models, right? They're not meant to be physically meaningful in a theory sense. So we have these parameters. So the sum of these parameters is not arbitrary because they're chosen such that archaic information criterion, pops out. But how you penalize for number of particles versus number of branching ratios versus number of production modes, this is arbitrary. And we thought we would choose something that kind of, sort of from a physics intuition, kind of makes sense, but there is some arbitrariness that remains.
And does it impact? Did you try to change?
Yeah, we played a bit, yes. And we know that it doesn't change the picture completely.
But there is a kind of information from Julia to use it to the subject of future investigation.
Yeah. Actually, we'll probably go right exactly in the direction of what Marie-Hélène said, in the sense that it will be more Bayesian information criterion, because we want to penalize for if there's more stop searches. You have to have even a larger deviation. Yes.
Thanks. That was really interesting. I there's always something I struggle with this kind of genetic algorithm, which is right, it is a kind of genetic.
You can interpret it as such, yeah. And like the closer metaphor is an MCMC walk, but yeah, you can also think of it.
Well, because like exactly like I mean,
yeah.
So as a Bayesian as a statistician, like what I don't quite understand is, so you have to choose the branching ratios and the masses in a way, and that here you have to, there's some kind of prior on the implicit prior on these parameters that is not like, yeah, it's not explicit, right? Like for every time you make a modification, you do modify the masses and at every step, like you can modify the masses or in the branching ratios. And how do you do that? And like what prior does that put on this?
There's not really a prior. There is maybe an initialization, if you wish.
Oh. So how do you transition like at
yeah, in terms of an MCMC walk, are you asking what's my proposal density? Is that roughly?
I guess so. Yeah. Yeah. Yes. Something like that.
Yeah. There is
some implicit prior, because like the protomodel score, like it has a high score. The changes will be smaller than. So we say we are changing the mass, right? So depending on the score, we allow for larger or smaller changes on the mass. So if the score is increasing, you don't want to take big steps. Yeah.
Yeah.
So you take final steps. So there are implicit priors in that sense.
And they are physics intuition. So the proposal density is, so there is a lot of, I mean, we don't use the term, but in MCMC walk, you would call it a proposal density. And that is mostly defined by physics definition, not a rigorous mathematical definition.
Okay, and so then how do you quantify the error? Like, oh, sorry. I don't know, I just turned it off.
Sure.
It mutes when you don't use
it. Yeah, how do you, so you have a particular model, can you quantify the error, like basically get a posterior on the,
yeah, we can. We only did it sort of very roughly in this first prototype, but we have an MCMC walk, right? The advantage of an MCMC walk is that it's designed to give you posterior distributions of parameters. That's what we use MCMC walks in Bayesian statistics, right? It's not exactly MCMC walk, but we can easily turn it into an MCMC walk by taking out some aspects. Yeah, like the ratio hypothesis, and then we have a posterior. So our idea is we first find the Proto Models, and then we do a normal MCMC walk to quantify the errors, to get a distribution, to get the posteriors in this Proto Model space. For example, fixing a model and then only get errors on the masses, on the parameters of the model. Yes, we can do this.
Okay. One aspect is, of course, that that should be implicit. We understood, but it's not been spelled out.
What did we not say?
Explicitly, is that of course that the number of dimensions of the parameter space varies while you walk through the parameter space.
We didn't say that.
Yeah, exactly.
That's why it's MCMC,
yeah.
right? Not really a remark of just
yeah.
Because the dimensionality of the problem changes each step, or can change.
Yeah. So in one biology paper, this was called transdimensional. This notion of this varying dimensionality of your theory space. Whatever the word, the dimensionality is not fixed.
Yeah.
Or very high dimensional but sparsity being imposed. You can have both interpretations.
Sort of imposing that sparsity.
By actually, defining, Andrea had it in one, by actually, you basically define a very large space of all possible protomodels by fixing the possible particle content. So you could also think of, I think it's roughly 1,000 dimensions. So you could also say you have a 1,000 dimensional theory space. Theory. Huh?
Yeah, some are 0, let's say.
And then you impose sparsity, yes.
Okay, other questions?
Can we ask from Zoom?
Yes. Yeah, Jack. Hey.
Yeah, can you hear me? Thank you.
Yes, very well.
So I wanted to ask, so Monte Carlo methods generally famously have a sign problem on them. So I don't know if you faced this in your simulations or not. Probably not, because you're using the BSM, so your parameter of interest is always positive, I assume. But I wanted to ask, can you, like, with respect to the terms in your Lagrangian, your system is basically differentiably linear. So can you translate this into a differentiable function, linear differentiable function, and minimize this negative log likelihood that you were showing? If you turn your Monte Carlo method into that, then you will be able to use any machine learning methods, and maybe even with reinforcement learning, you can impose some group theoretical structures on your data.
I think these were four different comments / questions, right?
Yes.
Okay, the first one that I got stuck on is the notion of design. I will answer that, and I think Andre probably has more to say on the others, or Jonathan. So I think your worry was if you have a multimodal distribution and you have an MCMC walk, and this was your question about the sign, I assume. And yeah, so far it seems like the space. I mean, you know, the Proto model that actually came out is very simple, right? So far our theory space is still very small and very simple and very, you know, we feel like we have it under control, and it looked nicely convex and nicely well behaved so far. In the long run, what do we know? So that was question one, and then there was the group structure, reinforcement learning. Yeah.
There is a slide there over differentiability.
Right? Yeah, differentiability, but I think, was that the question? We have one slide about differentiability, because you mentioned it. So currently we have basically, you can also think of our algorithm first as a multi-level optimization, because it's an optimization within an optimization. You find the optimal set combination of results, but within the search of finding the optimal proto model. So it's maximization or minimization within a maximization, or maximization within a minimization. But it's gradient free. And gradient free, so far it still worked very well. Gradient free means you usually have an algorithm that actually performs much worse than if you have an algorithm that uses a gradient. The gradient is a big boon. One of the reasons why neural networks are so nice, because they're gradient based. This one is gradient free. So far, everything was simple enough that our gradient free algorithm still worked very nicely. We saw that it converged and so on and so forth. We will go to higher and higher dimensions. And then it might be more difficult. And one vision that we're pursuing, as you know, Jack, is to make the whole chain from the raw data, from the data or from the published result to the UV complete theory. Ideally, you know, in the long run, say 10 years or 5 years down the road, the whole chain is differentiable. And this is actually described with this slide, right? Ideally, you have theory parameters theta, you have your combined likelihood. Ideally, it's sort of the likelihood, ideally we would describe all of LHC searches or even more. And ideally you would have the gradient of your full likelihood with respect to the fundamental theory parameters as this, you know, chain rule of differentiable objects.
So one question.
Yeah.
How would you make the addition of different particles differentiable?
Yeah, very good question. Very good question.
The rest I can understand. Smooth parameters, but that one is discrete.
That one is discrete.
I would say with respect to the terms in the Lagrangian, your model will be differentiable. So with respect to the terms, your model is linear, right? So you have only the constants, let's say, to scale each term. So your scale, your constants will be free parameters, and with respect to them, you can differentiate your model, I believe.
But to answer also, there are tricks to make like these discrete types of variables also differentiable.
I use a.
Yeah, sigmoid, wash out, pretend that you can add half a particle.
Yeah, there are certainly tricks. I was just asking what you think.
Yeah. We would have to employ some of these tricks, yes. There's weak derivatives. My understanding is that these autograd tools actually already implement many of these tricks. But yeah, I have not investigated. Yeah. Jack, you had more questions? I don't know.
No, I'm happy. Thank you very much.
How many technical questions we discussed in the...
Yeah, internally.
Any more questions in the room or also? Okay. In any case, Wolfgang and Andre are still here until the end of the month. Until the 25th.
No, also in the fund. 24 hours, within 24 hours.
All right. So there's opportunity whenever you want to pass by for a discussion before the coffee.
Thanks again and
Thanks.